Hi everyone, my name is Paul, and before I hand over to Michael, I just want to make sure that we can all agree on basically two things. The first one is why BlueChi had to be developed in the first place and what value it brings to the automotive industry. So, to put things into perspective, we are at Red Hat developing an in-vehicle operating system. It's done the Red Hat way, it's open source, but we're also aiming to get functional safety certification. That means we are operating in a highly regulated environment, and that also means that we cannot just do whatever we want. We need to have strong requirements on the stuff that we implement, and if we add functionality that does not add value or is not required, we introduce risk, and that needs to be avoided. The second challenge that we face is if you look at the current and future vehicle architectures, you basically see that it will still feature multi-node challenges. So workload will probably run in a distributed setup, even though it's moving to a more central place. And the combination of those two challenges has not been addressed in the open source realm, so we decided to come up with BlueChi. And before anybody asks this question, why don't we just run Kubernetes in cars? The short answer to this is no. And the very long answer is probably that Kubernetes has been designed to guarantee the uptime of your web app. It's there to make sure that you can serve your customers, but it doesn't provide means to fall back to a safe, well-known state. It's eventually consistent, and it probably doesn't provide any guarantees on order of execution or timing of specific events. So we had to come up with something new. And actually, it's pretty simple. We are just going to leverage what's already there on our system. It's the init system, it's PID1. That's the thing that starts up all other processes on the operating system. And what it provides is a way to define application profiles. Those application profiles can basically be mapped to states in the vehicle. So you could have a state for, I don't know, driving forward, reversing, and at each of those states, a different set of workloads is running, like the ACC functionality or the stream of your rear view camera. And systemd provides means to transition between those states so that you basically have something that could manage this kind of stuff on a local node only. But we are in a multi-node environment, so we developed BlueChi. And what it does, it is adding a tiny layer on top of systemd and enhances this for multi-node purposes. So, for instance, you would be able to define dependencies between services running on different nodes. And with that being said, I just hand over to Michael, who is probably more of an expert to explain all the technical stuff than I am.
Thank you, Paul. Well, we'll see about that. Next slide, please. Next one. Yeah, so what components did we decide to implement for BlueChi? Well, we came up with a two-component approach, namely the controller and an agent. The agent we will be running on each machine that we want to manage. Each machine we want to manage, and the agent then will go ahead and connect itself to the controller, which can be running on the same machine, but also, of course, on a completely different one. The BlueChi controller can then go ahead, send commands to the agent, which this one then forwards to systemd, and by this setup, we can already control services remotely. The last, or the third point here under the controller is no state management. So it's important to note that BlueChi, or the BlueChi controller, does not know the final desired state of a system. We are just the facilitator to enable external applications to reach the state. Of course, we can still provide the status of individual services to those external applications. And on this slide, we have a very basic setup for BlueChi. In gray highlighted are machines, could be bare metal, VM, container, you name it. And on the left one, we have a BlueChi controller running, which provides a public API on the local system bus, to which then external applications, in this case a state manager, can integrate to. So the state manager itself can be implemented in any language you want, be it Go, Rust, C, Python, you name it. And on the right side, we have two machines that we want to control, namely the agents. Those agents connect themselves to the local system D and are thereby able to control services locally. For example, starting, stopping, and so on. What the agents also do is they connect themselves to the controller. And important to note here is that each agent has its own connection with the controller, so it's a peer-to-peer connection, and agents among themselves cannot interfere with each other. And by this basic system, we can already control services remotely, starting from the state manager who knows the final state, which services to start on which nodes, submitting those commands to the controller, which it then forwards to the agents. But that's not all. As Paul briefly mentioned, BlueChi also added a new feature, which we call proxy services, which helps you resolve cross-node dependencies. Of course, the state manager, shown previously, would know the final state and how to resolve those cross-node dependencies, but this BlueChi feature enables you to resolve them by just relying on systemd mechanisms. So you wouldn't need any state manager. The second point here is quadlet. So if you run your applications bare metal, maybe you also want to run them in a container. And for this quadlet, which is a sub-project, I think, of Podman, you can use to easily write your own or containerize your applications and run them with systemd. As I mentioned, the API of BlueChi is program language agnostic. We also provide still type Python binding, so you can easily start prototyping against the API and write your own applications. The fourth point here, a Terraform provider, is currently something we are investigating. So you can easily set up a multi-node system by using this provider. Last but not least, QM. QM is also a project we are working on that provides you an isolated environment to guarantee you freedom from interference, which is important for FUSA, for example, to your applications and container tools. And it uses the BlueChi by, for example, deploying an agent into this environment and connecting it to a controller. And by this, the last thing I have to say, your mother was right. It's better to share, so if you have any questions, then please share them with us.
Thank you. So, any questions?
It seems to be very low level, actually, so I was wondering if you already have other projects or controller applications building on top of that. For example, I could imagine that this works together with Podman itself or something?
Yeah, so it's a, let's say, pretty new project, so we don't have many. But for example, like the QM project that I mentioned, which is already using it. Otherwise, well, with Portlet, it neatly integrates. But yeah, at least I don't know, not external ones, yeah, right.
And another follow-up question, does it also somehow provide means to actually transfer the workload binaries, for example, to the target node, or is it just about starting them?
You could run a service that does the transfer of the application.
Yeah, sure, I can write everything I want,
Yeah,
but so it doesn't.
it doesn't.
Okay, yeah.
It's out of scope.
Any further question? Otherwise, thank you guys. Really nice. So it's BlueChi Wawa, right?
Yes, exactly.
Great. Our next speaker, Angelo from Zetascale.
Okay, so it works, and it works smoothly, at least so far. So that's already good. Okay, so nice to be here. A few things to share with you. So first of all, thank you for making Zeno an SDV project. It's not a new project. We've been around for a few years, not necessarily forever, but for a few years, and we are coming from a sister community, which is the IoT community. So as we are new, right, as any gentleman, I owe some introduction and some context to let you understand why we are here and why that might be interesting. And I see many friendly faces. So hello, everyone. Long time no see. Okay, so why Zeno? When today you try to build a system that spans from the microcontroller up to the data center, and a car is that kind of system, right, as it is a robot and so on and so forth, this is what you end up with. Some people might like it, but unless your surname is Frankenstein or Frankenstein, if you get the pun, then this is ugly. And that's what we do today, right? Because putting together a system that goes from the microcontroller up to the cloud, only for getting some data flowing, it's a patchwork. It's putting together multiple protocols, and it's really painful. And it's not just a pain that we have heard of. It's a pain that we have been through, because as a company or as team, right, we were involved, for instance, in some of the earliest smart city project. Connected Boulevard was 2010 in Nice, if any of you recall about that, and then Barcelona later on, and so on and so forth. Things get even worse if you try to deal then with data at rest. So how about storing the data? Well, everyone stores it in the cloud because trying to decentralize the storage of the data, it's very complicated because then go figure out where the data is. And if you're old enough, or if you did an engineering degree in telecommunication in the old days, so at least in my days, you know that something similar to the situation where we are already happened. And that was happening in the early day of the internet. In fact, the ARPANET. Back then, there was not a single protocol. And schools like Stanford, Berkeley, the MIT on the East Coast, BBN, and so on, AT&T, they all had slightly different protocol or completely different protocol. And communication in the ARPANET meant having gateway across many networks to make them communicate. This is how we build today our systems, okay? And that was a problem because you end up to n-square connectivity issues. And in the end, IP, which by the way, I mean, I don't know, especially the younger people, if you realize that it's technically an heresy to run IP on a local area network. IP was intended as the internet working protocol, but again, it's not a course on telecommunication network. So IP became the one protocol that put everything together. And so you might say, okay, so we have the answer, it's IP. Well, not quite, because when the ARPANET was introduced, and I hope I'm not boring you with this history of telecommunication networks, but ARPANET was introduced to remove a strong limitation that there was in network back then, because back then networks were circuit switched. Literally, you were establishing physical connection between communicating endpoint. And that was very fragile because if you cut it, no more communication, right? And so we moved from a circuit switched into a packet switched network, but the abstraction remained the same. It was host-centric. As I need a phone number, to call Young, right, I need an IP address to communicate with a host. But this is not how we build our application today. Our applications are data-centric. They are name-centric, right? We name data. And this is why we end up with a proliferation of higher-level protocols that is solving the problem that we have in different segments, but doesn't work end-to-end, okay? So this is why we did Zeno. But before getting there, let me try to share some news about Zeno. And, well, some of them incidentally impact Zetascale because we are the company that invented the protocol and some of the main contributor. So this year, we were ranked as one of the top 10 automotive startups in V2X just because of Zeno, okay? If we move to robotics, and there is an inherent cross-contamination between robotics and automotive, we heard on the Adore talk they are using ROS 1, moving to ROS 2, and we hear very often that OEM in automotive are using ROS in R&D. Then they can't actually take it today to production, but there are intent of convergence. We will see what will happen in the next few years, but as we will see, there has been already evidences of technological convergence, and I'll give you a few more. So in 2022, Open Robotics was considering Zeno as the future of robotics and the new hope for robotics communication. Why? Because up to that point, most of the people were building standalone robots. And currently, the technology used for communicating in ROS is DDS. Those of you that are familiar with me know that I was one of the guys that started DDS standardization in early 2000. But DDS was not designed to operate on wireless network, was not designed to operate across the internet. And so they started struggling quite massively as soon as robots started moving and communicating over Wi-Fi, over 4G, and so on and so forth. Other interesting recent adoption, now it's almost 1 year, adoption of Zeno was from the ITU, the International Telecommunication Union. So a couple of years ago, there was a focus group, that's what FG means, that was tasked to look at protocols, all available protocols, and try to figure out which one was the most appropriate for intelligent transport system communication. And you can read from here or download the report because it's public. The conclusion after 2.5 years of research was that Zeno was the only protocol satisfying all the use case. What was the breaker? This use case here. In this use case, you have autonomous car that cache into each other, and you want to be able to understand who was the fault. And again, machine see whatever they see. There might be a bug in their perception, but they don't necessarily lie yet. So in this case, if you might look at the reconstruction of the environment that led to the accident, maybe you cannot tell who was wrong. And so you need digital witnesses. So from a data perspective, this problem is trivial because I have a collection of databases somehow distributed and moving around, but I know exactly how to express and solve the problem with a single query. It's a spatial temporal query, okay? I'm interested in this data set in this spatial area between this time and this time. Simple to express, very hard to implement with anything else that isn't Zeno, okay? And that's what led to that adoption. Amazon recently has written about and analyzed various protocols and once again pointed out the advantage of Zeno for IoT. But I want to get to a recent evaluation, which I think is the most important for automotive. So in 2022, as you saw, Open Robotics identified Zeno as the future because of some problem they were having with the current protocol. So there was a process, a little bit slowed down because eventually Open Robotics was acquired by Google, Intrinsics. I don't know many of you are familiar with it. But anyway, long story short, eventually the process after the acquisition resumed, and they did a systematic evaluation of all the protocol available on the market. And they also asked the community what they would have liked to see in ROS for next generation communication protocol. The user asked for ROS and the technical for Zeno, and the technical evaluation also ranked Zeno first. The result is that Zeno will be the first non-DDS-based RMW of ROS 2, and probably what will become, going forward, the solution for scalable robotics communication. So what has all of this to do with automotive? Well, what is a car if not a big robot? And especially if you think about autonomous car, I mean, in the end, they are robots. And there has been cross-contamination between the two industries. I would argue that if DDS is part of AutoSAR today, it's because of robotics and because the use that 15 years ago or 10 years ago was done in robotics. Robotics is moving to the next technology, and I think it would be interesting through the SDV to make sure that instead of suffering all the problem that you will suffer if you try to do V2X with the current technologies, right? We actually anticipate the convergence, and that's where we would like to help and contribute. So in terms of overview, Zeno is a kind of a strange beast because it really blends two protocol technology, pub/sub and named data networking protocols. So it provides you with abstraction for pub/sub and distributed query, okay? And does that very, very efficiently. We are certifying our protocol ACLD. So certification should be available Q1 2024. So that's an important news. In terms of where we run, we can run as low as a data link and anywhere upwards from a data link. We are written in Rust, but as of today, we are certifying the version that runs on microcontroller that is written in C, because although there is some important work for certifying Rust application, we are not yet there, at least for the level of Rust that we use. We have built-in support for shared memory and zero copy. So you don't need to add a third-party dependency to have zero copy. And in terms of networks, again, you can run on top of an IP stack, you can run on top of QUIC, you can run on serial, you can run on shared memory, you pick it. And if there is any other transport you wish, that's possible. And by the way, we run on very small devices, and our minimal wire overhead is 5 bytes. Only 5. I can explain how we do it. And by the way, there is a talk tomorrow on wire efficiency in which I'll explain how we get there. We run on your favorite target, both in terms of enterprise OS, Linux, macOS, QNX is coming up, it's in beta, as well as embedded target, Zephyr, Embed, ESP, Arduino. And as automotive target, we support, as of today, MicroSAR. That is an AutoSAR classic. And that's obviously for MCU. In terms of topology, you have no topological constraint. You can do peer-to-peer, you can do brokered, you can routed communication, and there is the topology up on the right that seems very exotic, but we use that in robotics. There are some oceanographic applications that use Zeno where they have peers communicating over a mesh, and some less powerful robots that cannot play the role of a peer, pairing up with the closest peer and playing the client role with the peer brokering communication for them. And all of this is completely transparent, and you can decide at runtime whether you want to be a peer or a client. It's super simple to use. Those are full application in Rust and in Python. And we have plenty of connectors to existing databases. That becomes our storage backend that then you can query from anywhere on the network, and existing protocol, MQTT, DDS, and more are coming. In terms of performance, over 70 gigabit per second on a 100 gigabit network, and around 6 microsecond latency, okay, when you use the ultra latency profile. I'm going fast, sorry, but we have only 10 minutes, and I'm still on time, right? Yeah, good. So I can breathe. Okay. Daniel always tells me that I don't breathe, and I don't blink either. Okay, so our latest release introduces some ultra-low latency extension. So the way in which we can achieve the 70 gigabit per second, and actually we also have very good throughput for small data, is because we have some built-in very advanced network scheduling. But if you do network scheduling, that takes some time, and so it's away a few microseconds. So now we have option to avoiding the scheduling and going straight into the communication that is the ultra latency profile, that then you can combine with any of the supported transport. So you could do ultra latency on serial, on shared memory, on whatever you want. Some shared memory core protocol improvements, Kotlin API, so supporting Kotlin application, more importantly, Android and Android Auto, which is a very important target. New Wireshark plugin, now built in Rust and built out of the same code base of the protocol. So any change we do at the protocol, automatically the Wireshark is updated. And because of major requests from the ROS community, we already had a ROS1 bridge to Zeno for robot-to-robot communication, and we have released a ROS1 that was already provided 6 months ago. This is the general release, because there were a few things in ROS that we needed to fix before. Coming up, JavaScript API, support for Android in production, new ROS2 bridge, improved shared memory support, InfluxDB connector 2, finalization of our MQTT plugin, modularization of Zeno Pico, because we have some company that wants to put Zeno on sensor. And so the next release, you will be able to pick exactly the protocol mechanism that you want and compile a version of Zeno Pico that only has those mechanisms. So you can really tailor to the bare minimal. and integration with new protocol. So you have probably already seen that there are repositories on new protocol. I think Steve has a presentation later on today, but we're plugging Zeno also underneath new protocol. Now, if you like this and you want to help out, okay, there are 3 things that we typically get asked by the community, which we have not done yet, and we will not do the next release. Maybe will be the one after. But if you are in an urge to get it, then we would really like to see in the community also an OPC UA plugin, maybe not so relevant to SDV, but CAN bus and some IP plugin absolutely relevant for the automotive. So if anybody would be interested or happy to contribute, we are very welcoming. And if you have ever visited our Discord, you know that you get a response usually in 5 minutes to your question, unless it's 3 a.m. In the night. So that is it. So we are looking forward to contribute to the SDV family. Once again, thank you for allowing us in. And yeah, so that's it. Thank you.
So any question? Because you already answered mine about U protocol, but yeah. So no question from the audience?
Was it so bad?
No, it was very good. It was too good. There are no questions.
No, when there are no
No,
questions,
no.
either it's too good or it's too bad.
No, exactly.
But I'm pessimistic, so.
No, come on. Yeah, there is one.
Thank you.
Thank you.
Even you. I mean, I stole you the microphone. You don't want to impose over me the pain of a question. No.
Thank you. What about the support of time-sensitive networking?
We're working on it. Okay, so that's the short answer. And again, there are some limitations on the current switches that will be coming up on Zeno Pico first. Okay, yeah.
So my question is, you run in a classic AutoSAR stack,
Yes.
and how do you also have connections to what is adaptive AutoSAR and something like that?
So the short answer is yes. Okay, I can explain how. So first of all, for those of you that are familiar with AutoSAR, I need to give you a precise answer. In AutoSAR Classic, as of today, we have integrated Zeno as a complex device driver.
Yeah.
Okay, first answer. SCDD. It would be nice to be as a network element. We are talking with AutoSAR provider, we'll get there. But as of today, we are a CDD. Okay. Next, how can you use Zeno in a mixed environment? AutoSAR Classic on microcontroller, AutoSAR Adaptive on the ECU as opposed to the MCU. So we are also the company that makes Cyclone DDS, which is a DDS implementation. For that, we are building an integration in AutoSAR because it's part of the standard. And as in Cyclone, we have a protocol plugin, you can plug Zeno under DDS. And so on the network, when communicating with Zeno, it talks Zeno. And for interoperability with other DDS applications, we will talk Zeno. But there is no extra bridging, no extra hope. It's just, yeah.
An extra question on ASIL D certification. That will be a security element out of context or something like that. Okay.
Yeah, yeah.
Okay.
Okay, by the way, you had gorgeous question. Thank you very much. Okay, thank you.